So now let's go into the concept of what a confidence interval is and what confidence means. One thing that we need to keep in mind when we have sampling distributions, they're never really actually observed, but it can be useful to think of a point estimate as coming from such a hypothetical distribution. So understanding sampling distribution will help us to characterize and make sense of the point estimates that we do get to observe. This interval is going to serve to estimate how close the point estimate is to the population parameter. When we look at the confidence interval, it's going to be a range of values within which the population parameter is expected to occur. We can look at this for proportions or for sample means. When we're looking at it in terms of sample means, there are two different ways that we can compute our confidence interval. One is when the population standard deviation is known, and the other is when the population standard deviation is unknown. So starting with the interval estimate of a population proportion, the population proportion, pi, refers to the percent of successes in the population. So with this, the binomial conditions that we talked about when we first got into probability must be met. So number one, the sample data are the number of successes in number of trials. Two, there are only two possible outcomes. Three, the probability of its success remains the same from one trial to the next. And four, the trials are independent. The other requirement allows us to invoke the central limit theorem and employ the standard normal distribution so that we can use Z to complete our confidence interval. So when you're constructing a confidence interval for a proportion, you will take that proportion value plus or minus what we call the margin of error. And so your margin of error is your Z value multiplied by that standard error of the proportion. So to find the Z value, you're going to look at your Z table to find that appropriate Z value. So from our previous discussions about the normal curve, remember that 95% of a normally distributed population or sample will be between negative 1.96 and positive 1.96 standard deviations from the mean. And so what this table on the right is showing is if I want to have a 95% confidence interval, that means that 5% of the distribution would not be within the interval. Since we're taking the portion out of the middle, the portion that will not be within this interval, called the alpha, will be equally divided between the top tail and the bottom tail of the distribution. Therefore, you really need to look at half of the alpha value. So in the case of a 95% confidence interval, you will need to have an alpha of 0.05 split evenly between the top tail and the bottom tail. So that means that you're going to have 0.025 on the bottom and 0.025 at the top. So if I'm going to be using a cumulative probabilities chart for the standard normal curve, like the one that we looked at when we first started using probability in the area under the curve, I'm going to need to subtract 0.25 from 1 to get the value of 0.975. And when I do that, I see that this corresponds to the Z value of 1.96. And so that's going to be the Z sub alpha value that we see provided in the table here on the right. So let's look at an example. We've got Union representing the Bottle Blowers of America. They want to look at a proposal to merge with the Teamsters Union. Over 3/4 of the membership must approve the merger. We have a random sample of 2,000 members. We have 1,600 who plan to vote in support of the merger proposal. What's the estimate of the population proportion? So the first thing we need to do is calculate that sample proportion. And when we do that, we end up getting a value of 0.80. And so that's going to serve as our estimate of the population proportion. Now, remember, we're going to use a Z value of 1.96 for the 95% level of confidence. I know this question didn't specify 95%, but let's go with that for this question. And so when we do use the 95% confidence interval, we end up with a value of 0.80 plus or minus 0.018. And so if we interpret this, this says if the poll was conducted 100 times with 100 different samples, we expect the confidence intervals constructed from 95 of the samples to contain the true population proportion. And so this would be the procedure that we use for polling organizations, television networks, and surveys of public opinion on election night. So now let's go into the interval estimate of a population mean, and for now we're really just going to focus on the situation of sigma known. So typically we know the population standard deviation when we have a long history of collected data. So knowing the population standard deviation is going to allow us to use the standard normal distribution. And so when we do this, we rarely know sigma exactly, but oftentimes we can make an estimate based on having that long history of data. And so when you have a long history of data, you can use what we call the sigma known case to developing or construct that confidence interval. So let's look at an example. We have a sample of 100 heights, and it turns out that the average is 5.77 feet. What's the population mean, or the average of all heights? We don't know, right? Because we only have a sample. We don't have everybody. So we have an estimate of that population mean as 5.77. So X bar, or our sample mean, is a statistic because it's the sample mean. Okay, so we're going to begin by assuming that the population standard deviation sigma is known. That may seem strange, but we don't know the population mean, but we do know the population standard deviation. We'll take care of this later when we come back to it, where both the mean and standard deviation are unknown, which would be a more usual situation. So here, picture number 1 can be any shape if the sample size is large. So what we want to know is how good or reliable or precise whatever the estimate is. And we can provide this answer by using a confidence interval for the population mean. And we end up saying something like we're 95% confident that the population mean lies between 5.72 feet and 5.82 feet. And so 95% is what we call our confidence level, and you get to choose what your confidence level is going to be. So our sample results would be of a sample size of 100. Our population mean is 5.77 feet. And notice that that would be in the middle of the confidence interval that we talked about in the other, on the previous slide. Your sample mean is always going to be the center portion of your confidence interval. As a rule, the more narrow the interval is, the more reliable or precise your estimate's going to be. So if I charged your company $10,000 to estimate the average of all heights, and I came back and said, I'm 95% confident that the average of all male heights is between 2 feet and 10 feet, quite likely you would not be giving me any more return business, right? Because you already knew that the average male height was between 2 feet and 10 feet. So the whole point of using a confidence interval that's very wide is that your estimate isn't really going to be very reliable. So how do we find 5.72 feet and 5.82 feet anyways? So provided that your sample size is large, or you have reason to believe that the sample is normally distributed, then we can go forward with using the z calculation, where we look at x minus x bar over standard deviation. But now we're looking at sample mean minus our population mean divided by the standard error of the mean. So that would be your population sigma over the square root of your sample size. So basically what you're doing is you're taking your sample mean and standardizing it using the z-score. Okay, so suppose we want a 95% confidence interval for that population mean. We're going to start working a z problem backwards. Okay, so what we do is, we have our z table, and this is going to give us our values between 0 and positive z. Okay, so we draw our picture. The area in red is going to represent 0.95 because we're finding the 95% confidence interval. So in the z table, because we're going to look for 0.475, and that value is going to belong to negative 1.96. And since we need to have mirror images, they're going to be equal to each other. Okay, and so that results with having our lower boundary being negative 1.96 and our positive boundary being positive 1.96. So the general form of an interval estimate for a population mean is going to be your sample mean plus the margin of error. So now we're going to assume that our population mean is unknown. Okay, so the procedure is to get the sample from this population and find the sample mean, or x bar. And so this will be illustrated on our next couple slides using the sample mean of male height. So using the previous z-curve, we've got the following is true. The probability of negative 1.96 being less than our random variable z, which is less than positive 1.96, is 0.95. So because we know that value, the probability of that happening is 0.95. If we now substitute in our standardized value for our sample mean for z, using that z equation we saw a few slides back. So then, now you can rearrange your formula where you have the probability of x bar minus 1.96 sigma over square root of n is less than my population mean, which is less than x bar plus 1.96 times sigma over n. So basically, you have your population mean right in the middle of your lower bound of your confidence interval and your upper bound of your confidence interval. And so a 95% confidence interval for our population mean is going to be between x bar minus 1.96 times population standard deviation over the square root of our sample size to the upper end, which would be our sample mean plus 1.96 times the standard error of the mean. So in our example, we're going to assume that the samples or the population standard deviation is 0.25. And our sample results out of 100 observations with a sample mean of 5.77 feet. We end up with a 95% confidence interval of 5.72 feet to 5.82 feet. And so this slide is just showing you how you take those values and you can plug them in and then work it out to get to that final confidence interval. So here we are 95% confident that the average of all heights, or our population mean, is going to be between 5.72 feet and 5.82 feet. We are 95% confident that the estimate of our population mean, which in this case would be our sample mean of 5.77, is going to be within plus or minus 0.049 feet of that actual mean value. So that amount plus or minus is the amount that we added and subtracted to and from 5.77 to get that lower bound and the upper bound and that is called our margin of error. So when I'm looking at this, the sample results, n equals 15, which is a small sample. X bar is our sample mean. And S, these are all what we call statistics because they describe a sample. And the value for our statistics are our estimates. So the 5.72 feet is our estimate for our population mean, and the standard deviation of 0.31 is our estimate for our population standard deviation. Now, remember, things that describe our population are going to be referred to as parameters. So looking at the 90% confidence interval, the area in red is going to correspond to 0.9 since we're finding 90% confidence interval. So in the z-table, depending on if you have a cumulative z-table that goes from 0 to positive infinity or starts at 0, if your z-table starts at negative infinity and goes up, then you're going to be looking for the value of 0.95 to get that positive standard deviation value. But if it starts at 0, you're going to be looking for the value 0.45. Okay, so half of the graph is going to be 0.45, and the other, the two halves combined together is going to represent 0.90. So 0.45 is midway between 0.4495 and 0.4505. So 0.4495, which is those probability values inside the table, that's going to correspond to a z-value of 1.64, and 0.4505 is going to correspond to a z-value of 1.65. So if it's right in the middle of those two z-values, we can go ahead and use the z-value of 1.645. So now that we're doing a 90% confidence interval, we can replace the 1.96 with 1.645 when we do our calculation. So now we do the same setup. We do x bar minus 1.645, which is our z-value, times our population standard deviation divided by the square root of our sample size. And we can substitute our values in to get that final range of 5.73 feet to 5.81 feet. So what this means is we are 90% confident that the estimate of our population mean, which is x bar of 5.77 feet, is plus or minus 0.041 feet of the actual value. So when you're looking at choosing what your confidence intervals are, you've got to kind of think about the effect of it. So remember, your z-value is the value between z and 0. This is why they're calling it the z1 half. And so it makes it a little bit easier that way in terms of just keeping straight of what value you're looking at on your table. And so when you're doing this, it's usually easier to use a table that goes from 0 to your standard deviation as opposed to going from negative infinity to whatever your value is. And so when your confidence area interval is 80%, you're looking at an area of 0.4, so you're using a z-value of 1.28. When your confidence interval is 90, your area is 0.45 with a z of 1.645. But what I really want you to notice is when we go from a confidence interval of 95% to 99%, we have a huge jump in our z-values. And so remember, when you're doing this, you want to have as much confidence as possible. So typically, you're going to use the 90 or 95% confidence level. Wider limits can tend to make your results a little on the useless side. So if you have a $4 million budget with an error value of plus or minus 2 million, that can make it really difficult to do budgeting, right? So if you want to get more narrow limits and higher confidence, you can do this by using a much larger sample size. And so when we're talking about confidence, what it means is because 90% of all the intervals constructed using my sample mean plus or minus my z-value times the standard value of my error of my mean, that's going to contain the population mean. We can say that we are 95% confident that this interval is going to include my population mean. And so we call that 90% our confidence level, and the value of 0.90 is our confidence coefficient.